Okay, this is chapter 6.1, exponential growth and decay functions. Essential question, what are some of the characteristics of the graph of an exponential function? So it looks to me like we are done with quadratics for now and radical functions. Now we're going on to exponential. So what you will learn in this chapter is graphing exponential growth and decay functions and use exponential models to solve real-life problems. So let's take a look. Okay, so exponential growth and decay functions are exponential, and an exponential function has the form of y equals a times b to the power of x, where a cannot be zero. Okay, because if a is zero, then a times b would be zero, and no matter what x is, the whole thing would always be zero. So a cannot be zero. And the base b is a positive real number other than 1, because if a were 5, 1 to any power is just 1, and a to any times 1 is always a. So if b is 1, then we're always just going to get an answer of a. So it doesn't make sense to use b as equal to 1. So if a is greater than 0 and b is greater than 1, okay, if a is greater than 0, so let me give you an example. We'll do it down here. A is greater than 0 and b is greater than 1, and y equals a times b to the power of x is an exponential growth function, and b is called the growth factor. The simplest type of exponential growth function has the form of y equals b to the x. Okay, so that means a would be 1. So core concept, parent function for exponential growth functions. The function f of x equals b to the x, where b is greater than 1, is the parent function for the family of exponential growth functions with base b. The graph shows the general shape of an exponential growth function. So the x-axis is an asymptote, which means the function comes down and gets closer and closer and closer to the x-axis, but it can never get down to 0. It's impossible for it to get to 0. 0.000000001 maybe, but never down to 0. An asymptote is a line that a graph approaches more and more closely, but never gets there. So the graph rises from left to right, and it passes through the point 0, 1. So the y-intercept is 1 when we have the parent function. And the point 1 comma b. So whatever the base is, when you substitute in a 1, you just get the base value, because anything to the power of 1 is itself. So the domain of f of x is b to the x is all real numbers. Okay, so we can put any negative 0 or positive x into the function and find a value, but the range is always greater than 0. Y cannot equal 0 and y cannot become negative. Okay, so that is the parent function of a growth function. Okay, so now let's take a look at the other. If a is positive and b is between 0 and 1, all right, b can't be negative, but it could be a fraction, like a half, then y equals a times b to the x is an exponential decay function, and b is called the decay factor. Okay, so parent function of the exponential decay function, the function f of x equals b to the x, in other words, a is 1, and b is between 0 and 1. It's the parent function for the family of exponential decay functions with base b. The graph shows the general shape of an exponential decay function. So it comes from infinity, comes down, it comes down, it comes down, and as it gets closer and closer to the x-axis, but it can never get there. So the x-axis, again, is an asymptote of the graph. And the graph falls from left to right, passing through the point 0, 1. Y-intercept is still 0, 1, and then 1 comma b. So for example, if I had f of x equals 1/2 to the x, okay, 1/2 is between 0 and 1. That's my base. And if I substitute 1 in, I get 1/2. So if I go over 1, b would be 1/2. Okay, so you get the base b value when you substitute 1 in for x. The domain of f of x is b to the x of equals b to the x is all real numbers. So we can plug any x value in and it will produce a y value, but the range will always be greater than 0. X can never equal 0 and x can never be negative again. Okay, so let's take a look at some examples. Okay, so we're going to start really basic in example one. All we have to determine is whether it is growth or decay. So tell whether each function represents exponential growth or exponential decay. Then graph the function. Okay, so the first thing I'm going to do is determine whether each of these is a growth or a decay function. So let me switch back to my pen. So b equals 2. A equals 1. So think of this as y equals 1 times 2 to the x. 1 times 2 to the x, 2 to the x times 1 is just 2 to the x. So A is 1, B is 2. And when B is 2, if I go back, okay, if B is greater than 1 and A is greater than 0, A is 1 in our case, B is 2, then it is an exponential growth function. Okay, so A is greater than 0. So I'm going to put that A, 1 is greater than 0, and 2 is greater than 1. Therefore, this is growth. Okay, in this case, I have a 1 out here, so A equals 1, B equals 1/2. Okay, so if I go back here, if A is greater than 0, so 1 is greater than 0, and 1/2 is less than 1. Let me move this over. Okay, 1/2 is less than 1, but it's greater than 0. So when we have B between 0 and 1, and A is greater than 0, therefore we can conclude that this is a decay function. Okay, so growth functions look like this, and decay functions will look like this. So we're going to graph these now. So let me bring in some graphs. Okay, so here we go. So you make a table. It can be horizontal or vertical, T-chart. And we're going to substitute X values in. So let's just start with like a negative number, like -2. I don't know what is going on with this computer today. So if I start with -2 and I put it in here, now what we're actually doing is y equals 2 to the -2, which equals 1/2 squared. Okay, so to make that a positive, you do the inverse. Our rules for exponents, and 1 squared is 1 and 2 squared is 4. So I get a quarter. Okay, so there's a quarter. So I'm going to plot that point, go over to -2, and up a quarter would be right here. 1/4, actually, it's not even that high. That's a half. So this is a half, this is 1, this is 1.5, this is, no, it's going in increments of 2. Okay, so 1 is here, a half is here, so a quarter is right halfway between a half and 0. So there is -2 up 1/4. Okay, and then we choose another value, -1. And then, so you'll get the idea real quickly as to what to do. Y equals -1 is now my X. So it's 2 to the -1, which equals 1/2 to the +1, which is just simply a half. Okay, so go to the left, -1 is here, up a half is right here. Okay, and we continue doing this by ones. This is 0. So this is going to be y equals 2 to the 0, which is simply 1. Anything to the 0 power is 1. Most common mistake when asked in class, what's 2 to the 0? 2? No, 2. Every number you take as a base to the power of 0 is 1. 1,000,000 to the 0 power is 1. And remember the function rule. It's going to go through the point 1, 0, 1. This is going to be the y-intercept. And then 1 comma b. So in this case, our b is 2. So we're going to go over 1. It's going to be 2. 1 comma b, remember? So if you remember the rules, it also gets easier. Okay, so if I plug in a 1, I should get b, which is 2. And there it is. Okay, and then it's actually gets quite easy once you get to the positive side. So if I put in 2, that means 2 squared, which is 4. So I'm not even going to show my work. That's 4. So I'm going to plot the point 2 comma 4, which is right here. And notice how much quicker it's growing. And then finally 3. Well, 2 cubed is 2 times 2 times 2, which is 8. Okay, so I'm going to plot the point 3, 8. Okay, so the graph would have a line coming through like so. And I'm not even going to try to draw that, so I'll just bring it in. Okay, so I just brought this image in. And so we do have the point -2 1/4, -1 1/2, 0 1, 1 2, 2 4, and 3 8. And then we label this as y equals 2 to the x. Always label your diagram. Make sure you have y labeled and your x-axis labeled. Notice we go through the point 0 1 and the point 1b. Okay, so that's the graph, how to graph an exponential growth function. Now let's go over and take a look at the exponential decay and see what happens here. So this one I'm going to start at -3. And remember what to do. So it's y equals 1/2 to the -3, which equals 2 over 1 to the +3, which is 2 times 2 is 4, is 2 times 2 is 8 over 1 cubed, which is 1. So 8 over 1 is simply 8. Okay, so I get -3, 8. So I'll plot that point. -3, 8 is right here. And then just add 1 and go to -2. And I'm just going to show the negatives. Y equals 1/2 to the -2, which equals 2 over 1 to the +2, which equals 4 over 1, or simply 4. So we're going to get -2 comma 4, which is right here. All right, and then we go to -1. So we're going to get y equals 1/2 to the -1, which equals the reciprocal to the +1, which is just simply 2. Okay, so we are going to plot the point -1, 2. And then we're going to choose 0. But think of that, it's 1/2 to the 0. Anything to the 0 is 1, and we're going to go through the point 0 1. Okay, so we're always going to have 0 1 unless there's something added onto the side, which gives us a shift or something like that. Okay, so then we're going to go to 1. Well, 1/2 to the first power is simply a half. Okay, no need to do the work on that. So it's over 1 up a half, which is here. And then finally 2. So it's 1/2 to the power of 2, which is 1 squared over 2 squared, which is 1 over 4, or simply a quarter. So go over 2 up a quarter is right there. And this is going to come down like so and get closer and closer to the x-axis, but never reach there. Okay, so here it is better drawn. So we have the point -3 8, -2 4, -1 2, the point 0 1, the point 1b, and the point 2 comma a quarter. And we label the diagram or the graph as y equals 1/2 x, the actual function. Make sure you label your y and your x-axis. So that is a completed graph. As this gets closer and closer to infinity, the x, as x gets bigger, this gets closer and closer to 0, but never reaches it. That's called a horizontal asymptote. Okay, so I forgot to put this up. After doing your 2 core concepts, you should have been able to do number 3 and 4. And then after doing example 1, you should be able to have done 9 and 12. So pause the video here, do 3, 4, 9, and 12, and then come back to the video. Okay, example 2 is solving a real life problem. So it says the value of a car, Y, in thousands of dollars can be approximated by the model Y equals, so I'm going to rewrite this. So we have the equation y equals 25 times 0.85 to the power of t, where t is the number of years since the car was new. So if I have a 2010 car, 2011 t would be 1, 2012 t would be 2, 2013 t would be 3, and so on. So before I even start, I'm going to list what my values are. A is 25 and B is 0.85. And 0.85 is between 1 and 0. So this is decay. Okay, the value of the car is going to decrease as time goes by. Okay, so A says tell whether the model represents exponential growth or exponential decay. So this is A, done already. You write this function. Okay, identify A, identify B, and determine if B is between 0 and 1 or greater than 1. It was between 0 and 1, so it's decay. Part B says to identify the annual percent increase or decrease in the value of the car. So T is given in years, and the decay factor is 0.85. Okay, that's the decay factor, B. The decay factor is your base B. So what you have to do for part B is you have to say 0.85 equals 1, that's 100%, minus 0.15. This is your decay factor, okay? Because T is given in years and the decay factors, I'm sorry, the decay factor is 0.85. So 1 minus 0.85 or 0.15 is 0.85. Then the annual percent decrease, the annual percent decrease is not the B, but what adds up to get you to 1. So the annual percent decrease is 0.15. And as percents go, you move the decimal 2 places to the right, and that is equivalent to 15%. Okay, so this thing is decreasing at a rate of 15% per year. C says estimate when the value of the car will be $8,000. Okay, very simply, you write the function y equals 25 times 0.85 to the t. Okay, and then substitute in your given, which is t. So I rewrite everything else, 0.85, but then I have to, and the car, when the car will be $8,000. So actually I'm not solving for T, I'm solving for Y. Y is the value of the car. Y is $8,000. So I'm going to put my 8,000 over here. Okay. So I want to get 8,000 equals 0.85 T. All right. So we haven't gotten far enough into this course. In order to solve this, you have to do what's called a logarithmic function. This is the inverse of an exponential is a logarithm, and we're not there yet. So we need to use a calculator to do this. But the first thing I'm going to do is, well, no, I'm not even going to do that. I'm not going to try solving it. I'm just going to go to my graphing calculator. Okay. And I'm going to put the original function into the calculator. Okay. So let me do this. So I'm going to go to y equals, and I'm going to put 25 parentheses 0.85 close the parentheses to the power of x, and I'm going to hit zoom 6 to go from -10 to 10, -10 to 10 on the x and y axes. Okay, so my function is way over here, so I know it's not ever going to get to the negative here, because remember, it's years. You can't get a 2010 car in 2008. It hasn't been produced yet. So I don't care about values that are negative in our time. Remember, this is our t-axis, if you will. So I'm going to change my window to x minimum to -1, just so I can see my window here. So I moved it over to the y-axis, and there is my function here. So I want to go higher, and I want to go to the right more. So to go higher, you want to go to a maximum, and I will change my y minimum to -1 because we can't ever cross the x-axis. And I want my y maximum to be maybe like 30. And then let's take the x maximum out to 30 as well, just to see what happens here. And now I get a better picture of my graph. Beautiful. There it is. So obviously the car was brand new right here. And as the years go by, the value of the vehicle decreases. So I'm going to use my trace function. So I'm going to hit second trace, and I want to find a value. So I'm going to hit enter. And we know that X is, we want to know what Y is. Or, I'm sorry, we can't do it this way. We have to, I can't put an X value in, I'll just be guessing. So I'm just going to hit the trace value. And here's X 14.5. Well, we want X to be, estimate when the value of the car is 8,000. We want to focus on our Y. And when Y is 8,000. So I'm going to move over this way. And when is it going to equal 8,000? Which is 8. This is Y in thousands, by the way. So there's 5.89, 5.58. So I want to go larger. So there's $6,215.78. Okay. And I keep going. There's 7,000. There's $8,126.04 or 5 cents. So it's approximately 6.9 or 7 years. So I would say after approximately 7 years, the car will be worth $8,000. Okay, so that's how you use a graphing calculator. So let's recap. You plug the function into the calculator. You adjust your window so you get a nice view of the graph. You hit the trace button, and Y is in thousands, 8,000. Because if I go up here to 0, if I get X to be 0, which is right there, there's my $25,000 car. Okay. The car was new, that was $25,000 when it was new. That's my A. And as the price drops, or as the time goes by, the price drops. Okay, so that's how you do example 2. So now you should be able to do problem number. Okay, there it is. So you should be able to do problem number 21 now. Okay, example 3, writing an exponential model. So it says in 2000, the world population was about 6.09 billion. And then it says during the next 13 years, the world population increased approximately 1.18% each year. So that's all the data that they gave us. And now we can write a function from that. So it says write an exponential growth model, A, giving the population Y in billions. Okay, there's the key right there, in billions. So 6.09 is 6,090,000. Okay, so during the next 13 years, the world population increased. So it's a growth function, and it's 1.18% each year. So the initial amount, so for the first part to write this, I want to know what A is, and that's our initial amount, and that is 6.09 billion. And the percent increase is, okay, so now I'm going to introduce a new variable. We call it R. Percent increase is R equals 0. Now that's 1.18%, so be careful. 0.0118. Remember, move the decimal 2 places to the left to go from percent to a number. So 2 to the left gives me 0.0118. That is our R. So the exponential growth model would be Y equals A times 1 minus R to the power of T. All right, so we kind of did this back here, right here. So if we did a model here, it would be our A times 1 minus 0.15, which is 0.85. And that's how we come up with these models. So it is actually 1 minus R. We just call the percent increase or decrease R. So now it's 1 minus that to get the B value. Okay, so we write the equation first. A is our initial value, so we're going to now substitute in our givens, 6.09 times, and it's 1, and this is a percent increase. Okay, so it's going to be, I'm sorry, it's not 1 minus R, it's 1 plus R. So it's going to be 1 plus 0.0118 to the power of t. So then I simplify my parentheses, 6.09 to the 1.0118 to the power of t. Okay, so there is our simplified exponential growth model right there. B is greater than 1, so it's growth. A is 6.09, so that's our y-intercept. A, so if you hadn't noticed already, A is your y-intercept, and B tells you whether it's growth or decay. And if you substitute 1 into the function, you're going to get B. If A is 1, but in this case you wouldn't. It'd be B times A. All right, so now it says using this model, you can estimate the world population in 2005. So it says estimate the world population in 2005. Well, in 2000 is t equals 0. So now I want to find out what this is when t is 5. So y equals 6.09 times 1.0118 to the power of 5. And I'm going to put that in my calculator. So let me open my calculator up and move this. And I'm just going to put that on my calculator. So I'm going to hit clear, and I'm going to put 6.09 parentheses 1.0118 close parentheses to the power of 5 and get a value. So y is going to equal, or it's going to be approximately, let's do an approximation. And it says estimate the world population. So it's going to be 6.46 billion. Okay, so we went from 6.09 to 6.46 billion in 5 years. Okay, so that's how you do that. And then B says estimate the year when the world population was 7 billion. So part B is we're going to take our equation, which was right here, and it's going to be y equals 6.09 times 1.0118 to the power of t. Now we're trying to find out the year. And again, we can't do this without doing logs, so we'll have to use our calculator. And when y was 7 billion. So 7 equals 6.09 times 1.0118 to the t. We're trying to find what t approximately is. So I'm going to go to my calculator and go to y equals and put my function in, 6.09 parentheses 1.0118 to the power of x, and graph it. Okay, notice how slowly that's growing in this case, because this is, so if now if I hit trace, if I go all the way back to the beginning, that's when x is 0 times 0, and that's going to be our population. So when x is 0, we're at 6.09 billion. And we want to know when x is 7. So I want to go all the way out here to 4, 5, 6. Here we go, right here, 7. 6.9 is pretty close to 7. So our so it's going to be about 6.5 years. So I'd say approximately 6.5 years. All right, so if we started in 2005, this would be 2011, and it'd be 6 months after. So June of 2011 approximately would be 7 billion. Okay, if I did 6.5, if you round to 7, it'd be about 2012. Okay, so now that I've done this, you should be able to do problem number 23 in your problem set. Okay, example 4 is rewriting an exponential function. So this example says the amount y in grams of the radioactive isotope chromium-51 remaining after t days is y equals a times 0.5 times t to the power of t over 28. Okay, so the first thing we're going to do is just rewrite the equation. So I'm going to put a times 0.5 to the power of t over 28, where a is the initial amount in grams. So 0.5 is our b. So this is decay. It's less than 1, greater than 0. So what percent of the chromium-51 decays each day is the question. So t days. So we want to know what this is daily. All right. So the first thing we're going to do is we're going to rearrange this. So I'm over off to the side. T over 28 is the same as saying 1 over 28 times, let me just show it the whole way so you see why it does that, times t over 1. Okay, I can do that. I can split this up because if I multiply this, 1 times t is t and 1 times 28 is 28. So 1 over 28 times t over 1 is the same as t over 28. But anything over 1 is itself, so then I can just rewrite this as 1 over 28 t. In other words, you can just take the numerator out in front and leave it as 1/28 of the numerator. And that's what we're going to do. So this is going to equal a, the a just stays there. And then I'm going to do, oops, forgot my parentheses. It's going to be a function with, it's going to be a parentheses within another bracket. So this is going to be, I want to do it this way right here. I want 1 over 28 in place of that 20 t over 28. And then what I'm doing really is just moving that outside because the power rule says to multiply this power by this power, the power of powers rule. And 1 over 28 times t is 1 over 28t or t over 28, which is what this is. Okay, so basically all we're doing is we're taking the numerator and moving it outside, but I explained all where that comes from. So that's step 1. So now we're going to evaluate that amount. So I need my calculator. So I'm going to do this, clear, and let's shrink this down. And I'm going to put in parentheses 0.5 to the power of 1 divided by 28 and hit enter. And that comes out to be a times 0.9755. 0.9755 to the t. Okay, so that's evaluating the power. And then we're going to rewrite this in the form of, remember the equation is y equals a times 1 minus r to the t. So how do I make that 1 minus? Okay, so 1 minus 0.9755 is 0.0245. So 1 minus 0.0245 is 0.9755. So I'm going to rewrite that as 1 minus the number that we were given. So this a comes down. So a never changes. Now I want to write this as 1 minus, well, what is this number? It's 1 minus 0.0245. And that's to the power of t. Okay, so that is the formula. And as you can see, let me highlight that. This value right here is r. Okay, so that's our daily rate. So in this case, r equals 0.0245, and that is approximately 2.45% when I move the decimal 2 places to the right. Okay, so that's how you do an exponential function and determine the rate of change. Okay, core concept, compound interest. Consider an initial principal P deposited in an account that pays interest at an annual rate R, expressed as a decimal, compounded n times per year. Okay, so n is the number of times per year. So if it was compounded daily, n would be 365, unless it's a leap year. If it were monthly, n would be 12. If it were semi-annually, it'd be 2, or if it'd be annually, it'd be 1. Okay, so number of times per year is n. The amount A, capital A, in the account after t years is given by A equals P times 1 plus R over N to the power of NT. So this is the formula we're going to start using for compound interest. Okay, so we're going to use this new formula in example 5. So it says finding the balance in an account. Okay, so you deposited $9,000 in an account that pays 1.46% annual interest. Okay, 1.46 annual interest for the balance. Find the balance after 3 years when the interest is compounded quarterly. Okay, so all this information is important. So we have a capital A, we have a capital P, we have an R, we have an N, and we have a T. We want to know what all of these are. And this is really fairly easy once we do this a few times. So let me go to highlighter. There's also this information here, 1.46 annually. All right, so deposited $9,000 into an account at the beginning. That's your principal P. So P is 9,000. Okay, so that's our P. The account pays 1.46% annual interest. That's the interest rate. So that is going to be our R, and we don't want it as a percent. So I'm going to change that to 0. And I move this 2 decimals to the left, and it's going to be 0.0146. So R is 0.0146 as a decimal, not a percent. Find the balance after 3 years. So time is 3. And compounded quarterly. Well, how many quarters are in 1 year? There are 4. So N is 4. Okay, so we have everything except A. So I'm going to use this formula. So if you didn't have this here, you'd write the formula, substitute the givens. To the power of N times T. So there it is. A equals 9,000 times 1 plus 0.0146 divided by 4 to the power of 4 times 3. Okay, so I'm going to simplify this. So A equals 9,000, 1 plus, and I'm going to use my calculator here to figure out what this is. 0. Help if I turn it on, clear. 0.0146 divided by 4 is 0.00365. All to the power of 12. Okay. And I could also rewrite that, simplify that some more as 9,000 times 1.00365, because 1 plus 0.00365 is 1.00365, and that's to the 12th power. So I get my calculator back, and I just put this in the calculator. So 9,000 parentheses 1.00365 close parentheses to the power of 12. Enter, and A, let me do this so I don't lose it. A is going to equal $9,402.21. Okay, we're going to round down. So I guess I won't do equals. It's an approximation. Banks do not give you partial pennies. Okay, there's no such thing as cutting a penny in pieces. So they would round that down to 21 cents. So $9,402.21 is going to be the balance after 3 years. Okay, so that's how you use the compound interest formula. Okay, so this brings us to the end of chapter 6.1, but I forgot to tell you that after doing example 4, you can do problem number 27. So use example 4 to answer 27, and use example 5 to answer question 37. And that brings us to the end of this chapter section, but I also want you to try 53 through 60, which are review questions. And that's the end of chapter 6.1. So thanks for watching, and have a great day.